In this video, we're going to talk about probability. Many times when you think about probability, you think about the chance that some specific thing occurs. Maybe you think about flipping a coin and the probability that it comes up heads, which would be, of course, 1 out of 2 or 1/2. Or perhaps you roll a fair 6-sided die and you want to know what the probability of rolling a 3 is, and of course that would be 1/6. However, in many situations, you're interested in looking at observations of what we refer to as continuous data, like time until a light bulb fails. Obviously, time is infinitely divisible, so you could have a light bulb that fails in 3 hours, or 5.5 hours, or 1.628 hours. There's infinitely many divisions, so saying that the probability is actually equal to a specific value is very, very difficult. So when we take random observations from this type of data, we get what's called a continuous random variable. So when we have a random variable of this type, I said it was difficult to calculate a probability. Well, really it's not all that difficult. What I meant by that was it's essentially that it has to be 0, because the probability that you're actually equal to a specific value is going to be 0 each and every time. However, we can estimate probabilities by creating what's referred to as a relative frequency histogram, and what that does is it calculates the probabilities that you fall within an interval of values rather than a specific value. So let's look at a picture here. So the purple rectangles here are what's referred to as your relative frequency distribution, or your relative frequency histogram, I mean. So what we mean by this is that, say here, if you want this interval that's between, it looks like what, 0.9 and 1.1. We just look at how the graph is divided up. When you look at this rectangle, the probability that you fall into that 0.9 to 1.1, the probability that you're in that rectangle is equal to the area of that rectangle. Okay. So similarly, any of these, say if you want to go from 0.5 to 0.7, that area would be 0.2 times 0.5, because that's the height of that rectangle. So you would get 0.1 in that case. So the probability that you fall into that rectangle would be 0.1. All right, so we're going to make these rectangles get smaller and smaller and smaller, or essentially fill in the area under the curve y equals f of x. Then the probability that we're actually between two of those values from a to b is going to be the integral of those values, because you think about, you would just take the areas and add them all up, and then take a limit because the areas are getting smaller, or the rectangles are getting thinner and thinner, smaller and smaller, and we turn into a definite integral. All right, so we call this type of function in this case a probability density function, or for short we call it a PDF of the random variable x. So say this more formally, we say that x is a continuous random variable. So the continuous part means that we're drawing these random observations from a continuous data set, and we're letting it vary because it's random. It could be whatever you want it to, so we just refer to that as x, and has a probability density function little f of x if it satisfies the following conditions. The first one is that your density function cannot be negative. It always has to be greater than or equal to 0 no matter what you put in there. Could be equal to 0. You could have something that's an impossibility. For example, if you're measuring lengths of narwhal horns, those can't be negative. So if you wanted the probability that something is less than 0, that would be equal to 0, because you can't have a negative length of something. If we integrate over the entire real line from negative infinity to infinity of the PDF, we get 1. Well, that makes sense, right? Because the probability that you're in between negative infinity to infinity has to be 100% of the time. That's what this would say. That's the probability that you're in between negative infinity to infinity. Well, that has to be guaranteed, so the probability has to be 1. The third condition here is that if you want the probability between 2 points A and B, we can calculate it through integration, like I mentioned. So this is how we get a probability density function. So it has to satisfy those 3 characteristics. So let's look at a specific example here. Let's let our f of x equal c times sine of x between 0 and pi, and we're going to claim that that is a PDF. The first thing we're going to do is we're going to find the value of c, and then the second thing we're going to do is use the PDF to calculate the probability that the value for x falls in between pi over 6 and 2 pi over 3. All right, so we're going to use that second property that we mentioned before, that when we integrate the PDF over the entire real line, we have to get 1. First, what we notice is that since it says that we're defined on the interval from 0 to pi, this, as long as your c is positive, will always be greater than or equal to 0, so we don't have to worry about that particular part. So the part we have to worry about is that second condition, that we really do get 1. Certainly, if we're outside the interval from 0 to pi, since we didn't explicitly define it, we're going to assume that we mean that the PDF is 0 on those values. So we just need to integrate from 0 to pi and solve this equation. So anti-differentiate and plug in our endpoints and solve for c, and we get c has to be a half. Alright, so now let's use this PDF to calculate the probability that the x value is in between pi over 6 and 2 pi over 3. Integrate over that integral. Here's our PDF. And again, just as before, take your antiderivative, plug in the endpoints. That's what you get when you plug in the endpoints. And if you simplify, you get square root of 3 plus 1 over 4. Notice that this is definitely less than 1, better be less than 1, right? Because we integrate over the whole real line, we have to get 1. So this is a probability it has to be less than 1. Now, one of the things you might be interested in probability theory is what happens on average. So on average, if you were to draw values over and over and over and over and over and over again and calculate the average of all those values, what should you expect to see for the value? Okay, so this is how you calculate the mean of a random variable, or this notation E of x stands for expected value of x. What would you expect to see over the long run? That's what expected value means. Well, remember the f of x is a density, so what you're calculating is a weighted average. You're going to take the x value and multiply it by the weight and then add it up. This is kind of like what you do when you calculate your grades. For example, say your homework is worth 20% of your grade, your in-class exams are worth 30% of your grade, and your final exam is worth 50% of your grade. If you wanted to calculate your final grade, you take your homework average times 0.2, your exam average times 0.3, and your final exam average times 0.5 and add them together. That's how you calculate that expected value, or excuse me, that average value for the whole class. You take the observation times the probability, or times the percentage, and that's exactly what we're doing here. We're taking the observation x and multiplying it by that probability density and then adding them all up. So this is how you calculate the mean of a distribution. So let's do it for that previous example. Calculate expected value, you take x times the PDF. You need to do a little bit of integration by parts here, so that's what your u and your dv would be. Here's just using your u times v minus the integral of v to u. Notice you get minus a minus, so that's what changes it to a plus. Find an antiderivative for cosine. Plug in your endpoints and simplify, and you get pi over 2.